Yesterday we learned about waves. Waves are a means of transferring energy from one place to another. That's the purpose of waves. That's a fundamental function of waves. And you jump into a swimming pool, you create waves, which transfer energy to all parts of the swimming pool. When a wind blows in the middle of the ocean and several hours later, somebody is surfing near the shore of the ocean, well, the energy was transferred from the wind in the middle of the ocean to the water near the shore. Energy transfers by waves. That's what they do. When you hear my voice, it's because energy is transferred from my throat, my larynx in my throat, to your ears. It doesn't mean that the actual particles are being transferred, but the energy is being transferred by those waves. Now, there's two kinds of waves, mechanical waves and electromagnetic waves. We deal with mechanical waves in Physics 20. Mechanical waves need a medium. They require something to travel through. Sound requires usually air to travel through. Water waves require water. Slinky waves require slinky. Okay, every mechanical wave needs a medium versus the electromagnetic wave, which can travel through the emptiness of space. There are two kinds of mechanical waves that we learned about. This is one of them. Do you guys remember what the name of this kind of wave is? This kind of mechanical wave, yeah? Good. This is called a transverse wave. A transverse wave, let's say traveling this way. This is the important part of a transverse wave. The transverse wave traveling this way experiences motion of the particles perpendicular to that. So if it's moving to the right, the particles are moving up and down. Now, how do you describe the motion of those individual particles? All of which, everywhere along here, are moving up and down. 3 words. How do you describe the motion of those particles? It's simple. Harmonic motion. Simple harmonic motion. The motion of waves is the simple harmonic motion of the individual particles within the wave, the repetitive motion of the individual particles within the wave. Now, let's label a few parts to this. You can already see that we have the crest and the trough labeled. The crest is the top of a wave or the peak of a wave. The trough would be the bottom or the valley of a wave. The wavelength we have labeled from here to here. Where else could we label wavelength? Well, let's start here. Let's start here. Tell me when to stop. Right, that's one wavelength as well. The distance over which the wave repeats itself, and typically that's going to be measured in meters. We also have the amplitude. The amplitude is the size of the wave. What's the size of the wave related to? How big the wave is measured from the equilibrium to the top of a crest or from the equilibrium to the bottom of a trough. How big the wave is related to what? One word. Energy, the energy of the wave. It's not a direct relationship. If you have a bigger wave, you have more energy. But if you have a wave that's twice as big, the energy is going to be 4 times as big. A wave that is 5 times as big, then you're going to have an energy that is 25 times as big. So crest, trough, wavelength, amplitude, all properties of this transverse wave. Next, we looked at the longitudinal wave, where if the wave is traveling to the right, the particles are traveling to the right and left in their own little area. They're all experiencing still simple harmonic motion in their own little zone. But this time the simple harmonic motion is parallel to the motion as opposed to perpendicular to the motion. A compression is, well, this is where the wave is kind of scrunched together in a rarefaction, not refaction. Rarefaction is an area where the wave is spread out. The compression would roughly correspond to the crest, and the rarefaction would roughly correspond to the trough. Got it? Finally, the last thing we looked at yesterday was the speed of this wave. We say that the speed of a wave doesn't typically change unless we go into a new medium. When light goes from air to glass, it slows down. But as long as light stays in the air, it travels at a constant speed. Or as long as it stays in the glass, it travels at a constant speed. Therefore, we can describe the speed of a wave by this equation, unless it switches media, unless it goes into a new material. It can be described by V equals d over t. But we also learned that from that equation, we can derive another one. V is equal to F times lambda. Do you remember what we called that equation? F times lambda? The name of it's not real important as long as you can use it. The universal wave equation, right. Speed of the wave, frequency of the wavelength of the wave. Finally, last question. Once produced, once the wave has been made, this property of the wave won't change. Ben. Good. Once the wave has been made, the frequency won't change. So if you made a wave at 10 cycles per second, 10 crests per second, or 10 troughs per second, then that's going to stay the same no matter what. Even if it goes into, the water wave goes to shallower water, the wavelength will change, the speed will change. But the 10 cycles per second won't change. Once a wave has been made, it is what it is in terms of frequency. Okay, yesterday we had 3 questions we were working on. We did the second question here. I want to do the third question. I want to do the third question here now, and if you want to, we'll do question number 1 as well. Okay, are we okay with number 3, or should we do number 1 and 3? Just 3? Sorry? Do both? Okay. Number 1 says orchestras use the note with a frequency of 440 hertz, A above middle C. I am not a music guy. I don't know my notes, okay, from anything. We'll trust this. A above middle C for tuning their instruments. The speed of the sound in an auditorium is 350 meters per second. What's the length of the sound wave generated by this frequency? Let's write down some given here. Here's my frequency, 440 hertz. Here's the speed of the sound, 350 meters per second. The length of the sound wave, what are we looking for? L? The length of the sound wave? Is that L? What is it? What is it? Lambda. It's that Greek letter. So we're going to say V is equal to F times lambda. Lambda is equal to V over F. If this wave was to go into an auditorium that was colder, the speed of the wave would change. And because of that, the wavelength would change. What wouldn't change? The frequency would stay the same. We're going to say V over F at 350 meters per second, divided by the frequency of 440 hertz. We do that, we should get the answer that's in the book, I think 0.795 meters. Good. 3. A fisherman anchors his dinghy in a lake 250 meters from the shore. The dinghy rises and falls 8 times per minute. What are they giving us there? Rises and falls 8 times per minute. Goes up and down. Ben? Yes, but probably better the frequency. If you wanted to find the period from this, you'd say 1 minute over 8 cycles. Probably better to get the frequency though, which we're going to say is 8 times per minute. What would the frequency in hertz be? 8 times per minute. How many times per second? How would you figure that out? Yeah, 8 over 60. And 8 over 60 is 0.1? 0.133, thank you. All right, what else we got? It takes a wave 3 minutes to reach the shore. So that's going to be a time, right? 3 minutes. We're going to convert that to seconds, 180 seconds. What is this 250 meters? Is that the wavelength? The length of the wave? Yeah, it's just a distance. Just because it's in the context of a wave doesn't mean that that's the length of the wave. We're simply told that this is the distance the boat is from the shore. What are we going to find? How far apart are the wave crests? The distance from crest to crest. The distance over which the wave repeats itself is known as lambda. Okay, so we're looking for lambda. The only equation we have with lambda is that universal wave equation, V is equal to F times lambda. Rearrange this to solve for lambda. We get V over F. We sub our numbers in. Oh, we got a problem. We don't know what V is. Any ideas? Use another formula. Who said that? Parker, which formula do we use? Good. So the distance that the wave travels is 250 meters divided by the time of 180 seconds. That gives me, what is that? 250 divided by 180. 1